Okie dokie. So today we're going to talk about sigma notation and being able to write what that expression is. So sigma notation is a way to express series in sort of a concise manner. It's the notation version of writing out a series. So instead of having to write term plus term plus term plus term plus term, we can write this notation that describes how we generate those terms, and it gives us a lot of information kind of in one nice compact punch. So some people call it sigma. It's the Greek letter, basically the Greek letter S, capital letter sigma. We've seen that before too when we did some things with standard deviation. It always denotes a sum. So when you see that Greek letter, big capital letter sigma, that's always telling us that you are adding something up. It's a sum. Other people, though, use the term summation instead. So like summation notation, using the word sum right in it because some people find that more informational because they know that that means a sum then. But whichever terminology you use, it's a way for us to describe the terms in this series. So let's talk through the notation. So I want to look at this half of the equation here. So this is the series that we're trying to describe. If I wanted to do A1 plus A2 plus A3 and so on, I would start with a term, so whatever number's on the bottom, that is the starting term number. So it's the starting term number. So instead of thinking of it as always A1, I'm going to say starting term. It doesn't have to be A1. You could start a series at term 7 and go to 12. You could start at A3 and go to A58. So it doesn't have to be A1, but it has to be the initial or starting term number, like where it is in line for that particular series. So whatever number is on top then, we're going to call that the ending term number. It's the term that you would end with. So if I'm starting at 7 and going to 12, I put 7 on the bottom and the 12 on the top, just so people know where my series starts and where it ends. The other most critical part of this notation is the AN part. That's the rule, the nth term, the way that we generate this series. So the nth term or the rule. So it's the equation part of this, I guess, but there's no equal sign at that part. But it's how we generate the terms. It tells us what the expression is we use to figure out the terms in that series. So just by knowing this thing in this lovely blue cloud, we're able to express any series we want. So I want you to see what that looks like. So for a situation like this, when I look at that, sigma means a sum, so it's the terms that I'm adding up. It's starting at term number 1, ending at term number 5, and this is the rule that I'm going to use to generate what those terms are. It's my nth term formula. Now if you look at that equation, it is linear. So when we look at this equation, it's really important to look at the rule and understand what kind of rule it is. It's linear with a slope of 6, which means in our lingo for sequences in series that it's arithmetic and it has a common difference of 6. I'm going up by 6 each time. So when I look at the series that I'm going to generate, it's going to be arithmetic. It's that linear relationship. Okay, so we're going to do what's called expanded form first, which is, what do you think of when you think of expanding? Things that are all spread out. We're going to do all the terms, like look at what that would be. So how do I find A1 in this series? Well, A1 is found by substituting a value of 1 in for n in my expression and simplifying. So 6 times 1 minus 5 would be A1 in this series. And then how would I find A2? Well, 6 times 2 minus 5. And then A3, 6 times 3 minus 5. And A4, 6 times 4 minus 5. And then A5 would be 6 times 5 minus 5. So I'm just finding the values in the series by substituting in the term number into the expression. And then I can figure them out. So for the first one, 6 times 1 minus 5, that would be 1. And then we'd have 7. And then we would have 18 minus 5 would be 13. I'm going to stop there for a second. Remember what kind of series this was supposed to be. Arithmetic, right? Common difference should be 6. It's always the same as the slope. Look at what your terms are doing. Up by 6. Up by 6. So for those of you who aren't too keen on doing a whole bunch of arithmetic that looks kind of complicated, how about just keep adding 6? So the next one would be 19. Yep, sure is. Next one would be 25. Yep, that sure is. This is what we call expanded form, what I just wrote. So expanding out all the terms to be able to see the series. So this sigma notation represented this expanded form. Now don't forget though, sigma means sum. When you see that capital Greek letter, it means you're supposed to be adding something up. So don't forget to go back and add up your terms, which I believe in this case would be 65. So that finite sum I can calculate. So sigma, great way to express a lot of information in one compact set of notation. Okay, so I want you to see something that looks a little bit different. What kind of rule is this one? Well, look where your variable is. It's up in the exponent. So this is exponential, or another way to say that would be geometric. What's your R value in this one? What are you timesing by? What's your base? Well, that's 1/4. Now that's going to tell us some really important information. If I know it's geometric with a ratio of 1/4, we have decay happening here. These terms are getting smaller and smaller and smaller. The limit exists. It goes to 0. These terms are going to get tiny. Okay, what else do you notice that's maybe a little bit different about this one that you didn't see in the last one? Hopefully your attention is being drawn to that. Infinite. That means the series has no end. It starts at term 1, so if I want to write expanded form, I can substitute a 1 in to find term 1. I can put in a 2 to find term 2. I could put in a 3 to find term 3. Oops, said 3 and I wrote it. Put in a 3 in for the power and find term 3, but I really can't ever get to the end of this series because it gets infinitely large. So I just do, if I asked you to write this whole thing, that would be really mean because you can't get to the end of this series. They're going to get super tiny, but you can't get to the end. So I usually, for my expanded form, like to show 3 terms because that way people can see what the pattern is. They can see what's happening, but we don't need to be excessive in how many that we're going to do. So for the expanded form part, just do enough so people can tell what the pattern is. So for the first one, that would be a half. Now, if you don't want to mess with this arithmetic, 1/4 squared, that's 1/16 times 2. That would be 2/16. Reduce it down, you get 1/8. Remember what your pattern is. Aren't you timesing by 1/4 each time? So just do 1/2 times 1/4, and we can get that number and keep going. And I think that's a faster way than actually doing the arithmetic itself. But whichever way you want to go, that's fine. Just know what your pattern is. Okay, now remember what sigma means. It's a sum. So we were able to write the expanded form, at least enough of it to see the pattern, but ultimately we're supposed to be able to calculate a sum. Well, this is infinite. My goodness, how are we supposed to calculate a sum if it's infinite? But it's infinite geometric with a ratio less than 1. So remember, that's decay. Those terms are going to get smaller. They're going to go to 0, and we can estimate it with our infinite geometric sum formula, A1, which is a half, over 1 minus the ratio, which is 1/4. So just be realizing that we can't do very many infinite sums at all. We can't do any sums that are infinite for arithmetic. Geometrics with a ratio bigger than 1, we're out of luck. But if that ratio is less than 1, we are in business, and we'd end up with a sum of 2/3. So these terms, as we add them up, the 1/2 plus 1/8 plus 1/32 and on down the line are going to get closer and closer to 2/3. So the value of the term when we add those all up. So be aware there are some things we can do with infinite. Okay, let's talk about another type of rule. I want you to see again, each one of these is for a different purpose. How is this one different? So for this one, the rule itself is degree 2, so this one is quadratic. So if you think about what the graph would look like, it's a parabola, vertex drop down 1. Now, but what's the other part that's unique about this one? Hope your attention is drawn to this. Starting at term 3 and going to term 7. How many terms would that be if I start at term 3 and go to term 7? Sometimes it's nice to have the visual so you can actually count. You can use your fingers. 3, 4, 5, 6, 7. That's 5 terms. 5 terms in that sequence. The biggest issue people run into is they see that 7 sitting on the top and like, oh, 7 terms. Not if you don't start at 1. If you're starting at 3, that's only 5 terms. So be aware what's happening with those values. Another thing people do sometimes, which is kind of interesting, is they'll start at term 3 to do their expanded form, which is fantastic, and they'll substitute that 3 in and they'll do their expanded form, but then they do 7 terms still again. Well, once again, if you're stopping at term 7, it doesn't mean that there's 7 terms necessarily, not if you start at term 3. So know where you start, know where you stop, so you can keep track of those values. So this only has 5 terms. So 3 squared minus 1. And then we have 4 squared minus 1. And then we have 5 squared minus 1. And then we have 6 squared minus 1. And then we have 7 squared minus 1. So it's only up through term number 7, which means substituting in 7. So it looks like that would be then 8, and then 15, 24, 35, and 48. And again, don't forget to do the sum. We need to add those up. We need to do that total. So we need to figure out what those values are all added up. So make sure we get that total there, which I think is 130. Yep, so we do our sum. Now, when I look at this series, it's important that you recognize how we know that this series is quadratic. So when we look at the actual terms that we get, we went up by 7, up by 9, up by 11, up by 13. So first differences aren't constant, but they're going up by 2 more each time. That means my second differences are a constant, and that's how I know that it's quadratic. We talked about one of those models when we were doing our limits. So being able to recognize quadratic sort of models is really, really helpful. A lot of people look at 8, 15, 24, 35, 48 and don't think it's quadratic, but remember that's coming from a 9, a 16, a 25, a 36, and a 49, but they're all 1 less, and that's why that rule works. It's 1 less than that value squared. So we have lots of different ways things can grow. All right, so let's take a look at kind of going the other direction now, so working backwards. I want to talk about how we can come up with if you have a series, how to write that in a form that makes sense for sigma. So going backwards. So things to think about. I have lots of information, so pause as you need to. But first thing I'd check for is if it's arithmetic. If it's a linear scenario, if you're going up by the same amount, fantastic, because we have an AN formula that we can use to help write that rule for sigma. So we can use that formula. Same thing if it's geometric or exponential. Great. If you know it's multiplied by something, we have a formula for that. We know what our R is. We don't have to worry about being intuitive or creative. We know that we can fall back on that plan. Factorial is another way that we've talked about growth or decay, depending on which way those terms are moving. So n factorial would be something else to look for. Be aware of those numbers. And then, of course, we've got our perfect squares, our quadratics, very common way to grow. And then we have our cubics, also a very common way to grow. So obviously, there's infinitely many more that we could talk about. Quartics, we could do absolute value. There's so many different ways you could have numbers. But we're focusing in on these particular types of sequences. So here's what we're going to do. We're going to try to work backwards. I'm going to give you the series, and I want you to see if you can figure out what the sigma would be to go with it. So on several of these, it's going to be really helpful if you pause the video, kind of think it through, and then check in with the solutions as I'm putting them up there, so you have a chance to think it before, just instead of just listening to it. The value in some of these is sort of your struggle through to try to figure out what's happening. So first thing I'd like you to do is figure out how are you moving from one term to the next. Try to look for the obvious things first, like arithmetic or geometric, because those we have formulas for. So for this first one, I'm going up by 4 each time, so it is definitely arithmetic. I have a common difference of 4. So if I know it's arithmetic, that means my rule when I write my equation has to be linear, and I know that my slope then is going to have to be 4, because that's what it's going up by each time. That kind of rise over run idea, up by 4, up by 4, up by 4. So let's see if we can come up with a rule for this then. When you write them, you can either start with the n equals on the bottom and put your starting term value after that, or some people just put the number. It really doesn't matter. You can do it either way. I think for starting to write these, I'm going to just keep doing n equals to help you remember that you're substituting the value of n in there. But let's see if we can come up with what this rule would be. So you know your slope is 4. So what if I just did 4 times n? Linear, right? So slope of 4 times n. If n is 1 for their first term, 4 times 1 would generate a 4. If n is 2, 4 times 2 would give you 8. 4 times 3 is 12. 4 times 4 is 16. 4 times 5 is 20. Looks like we're in good shape. So I could start at 1 and end at, this is term 1, 2, 3, 4, 5, and end at term 5. What I just kind of talked through is a pretty just kind of guess and check intuitive way to do it, kind of knowing what the numbers are doing. If you didn't have just an easy way to count to get to 20, if this was a really long series, if you know what your rule is, you can just set it equal to that last term and just figure out what n has to be like to work backwards. So if you couldn't just count to 5, which a lot of people obviously do, make sure that you think about how could I find that last term? What's another way I could do that? Now that works great for some people, but others just really need to have a plan. So you know what you can always do if it's arithmetic is you have an AN formula, just use it. So we have 4 as our first term, n minus 1 times our common difference is 4. I'm just going to go ahead and do my arithmetic, and I end up with exactly the same rule. And the cool thing with that is when you come up with this rule, you know it's going to start at A1 then because you used A1 to write that rule. So you know what term number it's going to start with. Because there are lots of different ways you can write some of these, and so sometimes it's just nice to know that, okay, I can write starting with term 1 if I use the formula. So don't think you have to be creative for that. All right, so let's try the second one. Same idea. I want you to see if you can come up with sigma. So try pausing the video. By what we did in the last one, see if you can figure out what would have to happen for this one. All right, so see if we figured out our pattern here. What are we doing each time? Looks like we're adding 3, so we have a common difference of 3. That means it's arithmetic again. So if it's arithmetic, that means I'm writing a linear equation, and my slope then would have to be 3. All right, so let's see if we can do that for our rule then. So if my slope is 3, that means it has to be 3 times n. And let's see if that works if I start at term 1. So 1 times 3 would be 3. 2 times 3 would be 6. 3 times 3 is 9. 4 times 3 is 12. 5 times 3 is 15. 6 times 3 is 18. So it looks like I'd be stopping at term 6. Again, if you know what your rule is, set it equal to that last term and just solve, and we can figure out what that ending number would have to be. So that's great. That's kind of the intuitive approach, looking at that you know it's the slope. So that's 3 times n has to be, and then just plugging in those term values. But once again, you don't have to be creative. You can just use your nth term formula, A1, n minus 1 times d, and just do that simplifying. So 3 plus 3n minus 3, that would still give us that 3n. And again, we're using A1, so we're starting at term number 1. So you have lots of options when you go through and do this. Okay, let's try a few more, kind of ramping up the ideas here as we go. So take a look at the next one. I want you to pause the video, see if you can figure out what the pattern is. What are you doing to get from one number to the next? And then let's see if we can come up with a strategy for it. All right, so hopefully you figured out that you're adding 2 each time. So there's a common difference of 2. So it's definitely arithmetic, which means it's linear. We're going to be writing a linear rule, a linear equation. And the critical thing in this is recognizing that the slope is 2. So regardless of what term you start with, the slope of this line has to be 2. So I know it has to be a 2n. Okay, now here's where people get super creative. Depending on where you want to start or stop, this isn't just multiples of 2, because if I just put in a 1 right now, if I start with term number 1, which a lot of people like to, 2 times 1 is only 2. And I'm supposed to be making a 5. My first term is supposed to be 5. So 2 times 1 is not getting me to a 5. So how do I make it get to a 5? Well, what would you have to add to 2 to make it a 5? How about a 3? Now let's see if that works for the next one. If I put in a 2 for n, 2 times 2 would be 4, plus 3, oh, there it is, 7. If I put in a 3 for n, 2 times 3 is 6, plus 3 gives me the 9. Works great. And where would I stop then if this is term 1? 2, 3, 4, 5. I'd stop at term 5. And again, if you're not sure, just set your rule equal to that last term and just solve. And we can figure out what term that would be. And again, I know when you can look at all of them and you see them all there, it's pretty obvious, but if you can't, we need a strategy. So that works great. So that's kind of the intuitive approach. People just look at, okay, if I put in a term 1, I know my slope is 2, how do I adjust that to get to the first term that I need to? What do I need to add or subtract? What constant would there have to be to make that happen? Awesome. But you know what? You could have done the formula as well. That works too. So you could have done 5 plus n minus 1 times the slope of 2. So 5 plus 2n minus 2. gives me that 2n plus 3. You don't have to be creative if it's arithmetic. You can just do it, and that's great. Now, here's the awesome thing on this one. Some people, and maybe you did too when you're looking at this, come up with something a little bit different. Having to add 3 is kind of a big constant. It's not terrible, but what if you started at term 2 instead? Now, if you started at term 2, I still have to have a slope of 2. I cannot change that, so it's still 2n. But if you put in a 2 first, 2 times 2 is already 4. What adjustment would you need to do to make it a 5? Well, you'd only need to add 1, or 2 less than what you did before because you're starting one term further. You've added 2 already one more time. So you could actually start at 2, but then what term number would you have to end with? Well, if I started at 1 and went to 5, 2 would have to go to 6, because 2n plus 1 to make a 13 would have to be 6. So I'm still having 5 terms altogether, right? 2, 3, 4, 5, 6. So still 2 terms. So that's awesome. I could do it that way. Well, what about this? What if I started at term 3? Could I do that? If you put in a 3, 2 times 3 is 6. That's 1 too big. It would be minus 1, and that would be going to term 7. So there are infinitely many ways you can actually do these depending on where you start. Just remember you have to adjust where you stop as well. And if you look at what the constants are doing each time here, they're going down by 2. Because each time if I'm starting one term further, that's that common difference one more time. So going back one more time. So there's so many different ways you can write these, but you don't have to be creative. You can go back and use the formula. It's great. All right, so I just wanted to show that there's lots of options. Okay, take a look at the next one. We're kind of wrapping up our first part of this with the arithmetics here. When people look at this one, they really freak out. They think, oh my gosh, what's going on? There's this fractions. It can't possibly be arithmetic. But you know what? It is. What do you do to get from one term to the next? You're adding 2/3. So my slope of that equation is going to be 2/3. It's arithmetic. It is linear. So you can start at term 1. We can do 2/3 n, because remember your slope is going to be the same as that difference. And then just make your adjustment. What do I have to do to get from a 2/3 to a 3 1/3? Well, I'd have to add 2 2/3. 2 2/3 plus 2/3 would be 3 1/3. But no worries. Remember, we can always do our formula, a1 plus n minus 1 times the common difference. So I can always go back and find that value, that rule. So 2/3 n plus 2 2/3 when it's arithmetic. Now, where's it going to stop? Well, we got dot, 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 so that means I don't have to figure out an ending number. That's actually easier than when they give you one. You don't have to figure out what those values are going to be. Okay, so we're going to finish up with the last 3 here that are not necessarily arithmetic. I want to get into some other types of sequences, or series. So take a look at the next one. What's happening as you move from one number to the next? Looks like we're timesing by 3 each time, times by 3, times by 3. So now it's not arithmetic anymore, it's geometric. We have a ratio of 3. That means we're going to be writing an exponential equation. But again, no worries, we have a formula for that. Okay, so let's see if we want to try to do it with term number 1. I'm going to do the formula first for this one. If you want to go ahead and pause the video, I'd like you to try to use the formula and write down what you think the nth term would be. Or if you can kind of guess and check to figure out a rule that would work, try that too. I want you to see what you come up with. So pause the video, see what you come up with. All right, so using the AN formula, which would be this for geometric, A1 r to the n minus 1 would give us a rule in here if I just wanted to go straight with the formula. And that's great. You absolutely can. It works wonderful. There you go. You have your an, because we know that that's the formula for it. How would we figure out this, though? We have this dot, dot, dot. I don't know how many terms are in between. I need to figure out the 2187. That means 9 times 3 to the n minus 1 would have to be 2187. Oh my goodness, how do we solve that? Well, divide by 9 first. Get the exponential thing by itself. We've done this before. Equals, I believe it was 243. So that must be a power of 3, right? And I believe that is 3 to the 5th. Double check. So that means if 3 to the 5th has to equal 3 to the n minus 1, what would n have to be? would have to be 6. That means that would be the 6th term. Some people might just keep timesing by 3, write out the terms in the middle, and make sure that you can just count them up, and that's great. But you can always set that rule equal to the last term and solve and find out what it is. So what I just wrote, that's absolutely fantastic. It works great. It's the rule. But now that's not what everybody comes up with. So I want to show a couple other options here for this one that we can talk about. Some people want to start at term number 1, and they're still going to stop at term number 6, but they don't see it like that. They don't see it as that complicated. 9 is a power of 3, right? That's 3 squared, that's 3 cubed, that's 3 to the 4th. So if they want to start with term number 1 and they know it's a power of 3, but they don't want it to be 3 to the 1st, they want it to be 3 to the 2nd, then just do n plus 1, right? Wouldn't that give you a 3 squared or 9 for your first term? And then when you do the last one, 3 to the n plus 1 to get 2187. Well, 2187, I believe, is 3 to the 6th power? 5th power. Let's see. Oh, no, 7th power. Let's double check. 2187, that would be 7th power, I believe. Yep. 3 to the 7th, double check on your calculator. So that means n plus 1 would have to be 7, so n equals 6. You could still figure out from that last term, but a lot of people think having a rule with just a single base would be easier. Now, I wrote 2 very different looking rules, but they both go from 1 to 6. So how can those possibly be the same? Take a look at this one and this one. How could they possibly be equal? Well, 9 is 3 squared, right? And 3 to the n minus 1. Remember, when you multiply with the same base, you add the exponents. If you add 2 plus n minus 1, you get n plus 1. It's exactly the same rule. It means the same thing. Super cool. All right, here's one more way. Love how we have all these different ways that we can do it. Maybe you came up with something else. Some people say, okay, I know it's 3 squared. How about I start at term 2? That means it would just be 3 to the n, because that would give me 3 squared or 9, and then 3 cubed. But then where would I have to stop? Well, if I'm normally going from 1 to 6, I better go from 2 to 7, and again, set that last term equal. I think this is the easiest one to solve on this end. 3 to the 7th is 2187. Cool, that means I go to term 7. So many ways to do this, but if you know it's geometric, you can always go back and use the formula, and you don't have to be creative. All right, so let's take a look at the bottom one here. So what am I doing each time? Looks like I'm timesing by 2, so my ratio is 2. That means it's geometric. All right, so let's try the formula again on this one. I know I'm going to start at term 1 then, which is very helpful because I'm using my formula. I'm using A1. Where am I going to stop? Even better, infinity. I don't have to try to figure out what that last term is. And then for my formula, A1R to the n minus 1, that would be 6. Ratio is 2 to the n minus 1. Not a lot of simplifying you can do there. I just have the rule that's going to generate the terms. Now, this one isn't as easy to combine and write in a lot of other ways. And if you think about it, it's because these two numbers, the bases, aren't the same. So we wouldn't really be able to combine them. So honestly, in this one, the easiest way to express this one, if it's geometric, is to just use that AN formula. Okay, last one I want to do for this part 1 is to see if you can recognize something completely different than even arithmetic or geometric. So take a look at this series and see if you can recognize what series of numbers this is. So pause the video, think about it, see if you can come up with your rule. Okay, hopefully you came up with n factorial. This is 1 factorial, 2 factorial, 3 factorial, 4 factorial, 5 factorial, and 6 factorial, which means I'm starting at term 1, I'm going to term 6. So we're trying to figure out what factorial that last number is. So remember, set it equal for that rule. So being able to recognize other sequences that grow is really helpful. But what if I had made the sequence this? 2, 3, 7, 25, 121, 721. Anybody know what that rule would be then? Something like that, right? So you can make those adjustments just like we did with the quadratic ones. So just trying to get you more comfortable with what those look like. So we'll do our day 2. I'll just do my last 2 warm-ups on that one, but this really gives us a great opportunity looking at sigma as a way to write those series.